Good morning, good afternoon, good night, everyone. I am Pierre Ferrand, will be moderator for this session dedicated to the Specialist Committee on Hydrodynamic Modeling of Marine Renewable Energy Devices. The presentation will be given by Dr. Bertelsen and for some 20 minutes or so, and then we will go for questions. So do not hesitate to post your questions via the web tool so that there is a lively discussion at the end of the presentation. So the floor is yours, Peter.
Ladies and gentlemen, welcome to the presentation from the Specialist Committee on Hydrodynamic Modeling of Marine Renewable Energy Devices. My name is Petter Andreas Bertelsen. I'm from Sintef Ocean in Norway, and I'm the chairman of this Specialist Committee. Next slide, please. I also like to add that we have a few other members of this committee, of course. We have Dr. Maurizio Collu, and we have Professor Ungu Shin, Professor Ye Li, and Dr. William Batten, and Mr. Bill Straka, Dr. Giuseppina Colicchio, and Dr. Keong Hong, Dr. Jean-Roch Nader, and Dr. Sylvain Bourdier, that have all been participating in this committee. I have also, we also have had 4 meetings during this ITTC terms, and 2 of the meetings we have pictures on this slide showing from one meeting that was hosted by the University of Strathclyde in 2019, and another one hosted by the Australian Maritime College also in 2019. The committee's main task has been related to, oh, sorry, I think you have to go to the next slide. So the committee main task has been related to developing guidelines and reporting on state-of-the-art on marine renewable energy devices. So this presentation will only give a brief overview of the work that we carried out during this ITTC term. For more details, I would like to refer to the final report. So next slide, please. The committee has been responsible for updating and revising 5 ITTC guidelines during this term. They include the guidelines describing model testing of wave energy converters or offshore wind turbines and current turbines. And there are 2 guidelines for uncertainty analysis of experiments with wave energy converters and current turbines. In addition, the committee has developed 2 new guidelines during this term, one on uncertainty analysis for model testing of offshore wind turbines, and 1 practical guideline for numerical modeling of wave energy converters. Next slide, please. The terms of reference for this committee includes reporting on full-scale installation of different marine renewable energy devices, and also monitoring and reporting on some specific issues related to wave energy converters, current turbines, and offshore wind turbines. On this slide, you can see the list of terms of reference summarized. So next slide, please. So in the first terms of reference, the committee is asked to report on full-scale installation of marine renewable devices. Can you also switch to the next one, please? Here is a list in a table of deployed or planned projects of wave energy converters from 2017 to 2020. The information includes type of technology, rated power, developer, and development status. Not all of these projects are full scale, since the industry are still mostly at demonstration stages. Furthermore, I would like to add that there is very little data and information available on these different tests, as well as virtually no information about the installation issue or survivability. The industry is still at early stage with very few commercial products, meaning that they still rely heavily on investment and grant funds, and of course, any issues or data obtained are therefore used sensitively and not published. Next slide, please. So as for the current turbines, there are some large devices being deployed around the world, but majority of them are only demonstrations to increase their TRL. Type of devices has not converged, but majority are horizontal axis turbines, Other types include kite-based systems, cross-flow turbines, and tidal fans. There are turbines who are bottom-mounted. They are tethered or supported by floating structures. Between 2010 and 2019, there were nearly 60 different current turbine devices deployed around Europe, with a total of 27.7 megawatt rated power, by which 10.4 megawatt were still in production in 2019. As for the survivability, some of the issues reported include structural and manufacturing issues of rotor blades. There were also some financial problems, and it can also be damage related to installation, both from towing and having a complex seabed. And there are also environmental factors such as turbulence and unsteadiness. Next slide, please. As for the full-scale installation of floating offshore wind turbines, the number of operating turbines has doubled since 2017, and the total installed capacity has quadrupled to about 85 megawatt. Spar-type platforms and semi-submersibles are the most mature types, but there are also new ones emerging such as damping pool barge, ballast stabilized pendulum, and others. Initially, the demonstrators were connected to the grid with a capacity of roughly 2 megawatt, but in later steps, we can see pilot wind farms with 3 to 5 units where the capacity is up to about 30 megawatt. Today, there are 2 operating floating wind farms with approximately 25 to 30 megawatt capacity each. The first one was deployed in 2017, which is Hywind Scotland Pilot Park, based on the Hywind Spar concept. And the second one is Windfloat Atlantic from 2020, where they use the Windfloat semi-submersibles. There are many more under development or being approved. Spars and semi-submersible types are fully proven today. The Hywind demo has been operating since 2009. And Windfloat Atlantic, the first phase, were operating from 2011 to 2016. There is also a 3 megawatt damping pool barge demonstrated by Ideol, which is installed in Japan. And this one has also managed to survive actually 3 Category 5 typhoons shortly after its installation. Next slide, please. So on the wave energy converters, the committee has been asked to report on new concepts. There are many concepts, but no technology convergence has been observed. And every company seems to have developed their own technology of devices and power takeoff systems. Just to give you 2 examples of devices, it's the vertical plates attached to a seawater pump, as in the wave piston, as given by one of the pictures on this slide. And also the pressure differential energy harvester through air inflated rubber membranes, as in the wave, as in the M wave from Bombora. Next slide, please. The committee has also established a practical guideline for numerical modeling of wave energy converters. The purpose of this guideline is to provide a methodology to assess the fidelity of the numerical simulations for wave energy converters at different stages of development. So in this guideline, you can find different numerical solvers that has been described, and also their range of applicability has been documented in detail. Next slide, please. The committee has also reviewed the progress on array modeling of VEX. In these form settings, the interaction between close-by VEX will give rise to complex wave fields that affects the power extracted by each device and consequently the total power output of the farm. There has been advancements in numerical and experimental modeling of arrays, and it has been summarized in the report. And the most significant advancement is the introduction of park optimization techniques that allow a multi-criteria choice of the VEX positions in the array. Next slide, please. The committee has also monitored the development in the WEC PTO modeling. The PTO modeling is still far from being standardized, mainly because of the diversity of the different wave energy systems. The difference in PTO simulation results can be significant depending on the modeling methods. Recent studies on PTO systems include the nonlinear, unsteady, and viscous properties of the PTO components, which are critical for the accurate performance evaluation. A series of benchmark tests to compare the numerical tools for hydrodynamic modeling of PTOs have been carried out by IEA Ocean Energy System Group since 2016, which included comparison of experiments and numerical simulations where different numerical approaches were considered. There is also continuous progress in development of integrated simulation tools and experimental techniques to consider the coupling effects between PTO components. Next slide, please. So as for the survivability of the WECs, it's worth noting that there is very little information being shared from the deployed full-scale devices related to their survival response. And also due to the complexity of WECs, there is still a strong need to update guidelines and standards for survivability testing of WECs. And as a conclusion, there is still a lot of unknowns related to survivability for WECs. We think also many of these things is just lack of information from those full-scale experiments as well. Next slide, please. So moving to current turbines, the committee has been requested to also develop specification for benchmark testing of current turbines. To date, much of the data and design geometries for current turbines have not been readily available in the public domain. More recently, a few experimental programs have been conducted for the purpose of validation of CFD predictions or to evaluate the impact of different facilities and test results on turbine performances. The databases are for some of these studies are currently or will soon be available online in the public domain. Although each of these databases provide valuable resources, specification for more complete future benchmark studies are needed. So during this ITTC term, general specification for benchmark tests of current turbines have been developed to understand bias between experimental facilities and to provide geometry, boundary conditions, and performance data for CFD validation and verification, and to provide data to assess performance scaling and predictions. Next slide, please. The committee has also investigated modeling of inflow turbulence and unsteadiness for model testing of current turbines. Replicating all the unsteady flow features is not realistic for a single test facility, and consequently, tests are done with simplification of the environment to produce unsteady flows for validation data. The following techniques have been reviewed in the literature and are summarized in the report. So I will just mention the different techniques. One is the use of towing tank with waves. Another one is the use of planar motion type mechanisms in towing tanks, the use of circulating water channels combined with currents, and the use of surface roughness on the bed of long flumes. The next slide, please. So when it comes to numerical simulation of current turbine arrays, some researchers still focus on improving existing methods to tune the accuracy of the wake structures, but a good number starts to develop methods to study other aspects of arrays, such as free surface effects and also the control algorithm. It can be understood that the accuracy of the wake on the free surface effect is in the same level of that of traditional methods, while that of the control study is less. And nevertheless, they require further experimental tests for validation. Additionally, tidal energy's potential impact on the environment has also received attention lately, and more investigation is expected to be conducted to understand this impact clearly. Next slide, please. So the final topic relates to the offshore wind turbines, and the committee has also reported on recent development of model testing of offshore wind turbines. The two main challenges with testing offshore wind are generation of high quality wind in a tank facility, but also the incompatibility between fluid and Reynolds scaling. The advancement of testing technology has moved from using simple disk to mimic the mean thrust to redesigning the blade profile to behave similar to the prototype at low Reynolds number, and more recently by combining computer simulations with physical experiments using so-called hybrid testing. As for the latter, the wind turbine load modeling is replaced by a numerical simulation, and wind loads are then transferred to the physical model through actuators. This way, one avoids any issue with incompatibility of scaling laws or generation of high quality wind in the tank facility. Can you go to the next slide, please? So there are mainly two different methods for hybrid testing of wind turbines in tank facilities. One method is to use software in the loop combined with fans or propellers mounted on the model to actuate the wind loads. In the first few examples, the SEAL methodology used a single duct fan to reproduce aerodynamic loads. However, this approach is limited to modeling the thrust force only. Later, the methodology has been further developed. The single fan has been replaced by a multi-prop actuator, which you can see on the right, the pictures to the right on this slide. This way, it is possible to model multiple components of the aerodynamic wind turbine loads, especially the yaw moment from wind turbine, which may be important for many design issues. Next slide, please. The second approach is to use cable-driven robots to apply the wind turbine loads on the model. Having multiple wires connected to land-based actuators and a frame at the top of the model makes it possible to model multiple load components from the wind turbine. This was initially applied in a model test at MarineTech in 2015, where rotor loads from wind from one direction could be modeled. The method was later refined to handle wind from any direction, which also allows for sudden change of wind direction as part of the conditions that can be tested. The illustration shows the layout of the wires and their connections to the frame mounted on the model. Next slide, please. The committee has reviewed existing regulations for offshore wind turbine designs. On this slide, there is a list of existing and relevant standards and rules that address the design of offshore wind turbines. The development of standards and rules and their application to offshore wind have allowed the wind industry to gain confidence in the floating wind turbine designs, and also these documents, they address how they are about to change from addressing prototype installation with a few units to a large-scale floating offshore wind farms consisting of many identical units. And the document would work as a central repository of knowledge and experience. So the next slide, please. So finally, the committee has also established a guideline on uncertainty analysis for model testing of offshore wind turbines. The guidelines are based on the ISO's guide to the expression of uncertainty in measurements, and the purpose is to provide guidance on the application of uncertainty analysis of the model scale testing of offshore wind turbines. Focus is on sources of uncertainty, and it includes a working example of an uncertainty analysis. So that was actually the last slide. If you can move to the next one, please, the final one. So I would like to thank you for your attention, and we are ready for question and answer. And again, I would like to apologize for the technical issues with the presentation itself. So thank you.
Thank you. So now we move to the question and answer part of the session. There is a written question by Arthur Reed. The question is the following: is not the gyroscopic effect of the rotating wind turbine blades an important factor in the platform motions? So, Peter, or one of your colleagues?
Yeah, I can partly try to answer and maybe ask some of the colleagues to back me up or supplement my response if they have other things to add to it. I guess the question refers to the model testing, where you use the hybrid methodology, where you simplify the problem and by that actually removing the gyroscopic effect. At least for the cable-driven robots, where you use wires to mimic the aerodynamic loads. Prior to these tests, it was done quite extensive numerical analysis, which has been published in a few conferences, to evaluate the different degrees of freedom that may have a significant or insignificant impact on the responses of the floating wind turbine. And one of the conclusions was that basically the gyroscopic effect was not that significant, so it was not that important to model. If it's deemed to be necessarily, it's also possible to add a kind of a rod with weights on it to have it physically to rotate to generate some gyroscopic effect as well. So I hope that's answered the question.
Okay, I guess so. Thank you. No other written questions, so I may have one of my own. In your presentation, you showed quite now a number of full-scale prototypes of floating offshore wind turbines. I have a very general questions. Is there a significant flux of information from these tests for feeding new developments in either in model experiments or in numerical modeling? Or those data, are they kept proprietary by the designer and developers?
As to my understanding, most of these tests are commercially driven, meaning that most of the information is also proprietary or a secret, commercial secrets. But I think that it's right now, I don't know, it's OREC, I think, in Orecatapult in Britain. They have a collaboration with Equinor regarding sharing some of the data from Hywind Scotland. Coming from SINTEF, we also have close collaboration with particularly Equinor about their development. So of course, on commercial basis, some data may be possible to access, but these things are not public available in general. I'm not sure, Maurizio, maybe you want to add, if you add, have any overview of any data that may be accessible.
Yeah, so yes, I confirm that Orecatapult here in Glasgow, you can register to Orecatapult and they give you access to the so-called data pod through which you can access some of the data of the 5 wind turbines that are deployed in Hywind Scotland Pilot Park. And I know that the company now operating the original first worldwide floating wind turbine that was Hywind 2 megawatt, it can be approached to get some data, experimental data relative to that prototype. But in general, as Andreas said, in general, these data are not shared. And that's why you have seen a number of initiatives at the international level called OC 2, 3, 4, 5, now 6, that are trying to complement this void of data. So the main way now to benchmark your code against other codes and to obtain some experimental data, but not full scale. These are at scale level. It's through these OCX exercises. And in the report, we have listed the internet address from which you can download this data to verify or validate your code.
Okay, thank you. There is a new written question, which is the following question by Kim Chow from StarScribe. Regarding new concept of wave energy converters, is there any comments on flexible material or structure, WEX?
Yes, I think I'd like to forward that question to either Shamrock or Josepina, if you may.
Yeah, sure. I'm not sure exactly what the meaning behind this question is, but the main one which we've seen was the Bombora M-Wave device and been tested at scale for short periods, which is a pressure differential. Now, in terms of those flexible material, which is used sort of a pump, we don't have, the device hasn't been tested at full scale yet. So we don't have really information about how it will actually work or what will be the long-term effect of this flexible material and how it will survive the sea and all that. So there's very, very little yet information around those flexible. It's very new. I was in the conference in ICOE and some ideas of using actual flexible material who have electrical property where the material becomes actually the PTO system, but that's very early research and there's nothing that I've know of practice been tested anywhere yet. So
I can say there are some pre-industrial projects like this, like the SC3 by single buoy moorings, or in a more academic circle, there was the what was the name, Anaconda. But there were no electroactive material in Anaconda. Instead, there was a turbine at the end of the duct. But
yeah, but it wasn't flexible material, was it?
The Anaconda, yes, I guess so.
No, it wasn't different pontoons we're talking about.
No.
That's
It's submerged flexible tube.
Ah, yes, yeah, that's right.
So maybe the question is about a lack of coverage of this type of wax in the report. I don't know. So, anyway, time is a bit over, so maybe if you want to add some final comments to these questions, otherwise we will close the session.
Yeah. Can I add one last comment about the flexible materials? Actually, the dielectric PTO has been tested in Reggio Calabria. They used it on an oscillating water column. So they were actually blowing this huge balloon on the top of the oscillating water column and extracting energy from it. But it is still at a low technology readiness level. Yeah.
And the cost is still very high, I guess.
Yeah. And the problem is also the water. If it gets in touch with the dielectric material. So
okay. So thank you for these last comments. So I would like to thank the whole committee for the huge work done and for the quality of the presentation and answers to the questions. So that ends this session. Thank you very much.
Thank you.